In the first two videos, we talked about stress. And I showed you, for example, this demonstration where you take a thin copper wire and a copper rod made of the same material, and as hard as I pull, whatever the largest force I can apply, I'm unable to stretch the rod. Whereas with some effort, but not all that much effort, one is able to pull on this copper wire and extend it. And they're the same material, so we'd like to have a property that describes the behavior of the material rather than describes or concerned with the size of the material. And so I can go from the small copper wire and understand how the large copper bar will behave by simply taking the force and normalizing it by the area to get stress. Well, today we're going to talk about the counterpart of stress. Stress is sort of the force or the driver of what's going on. And today we're going to talk about deformation or the strain that evolves from applying a stress. And so the topic of today's lecture is going to be strain, and it, like stress, has the same issue that we need to worry about size dependence. We don't want our information to be biased by the size of the object we're studying, but we want to do the proper normalization so that I can predict from deforming a small piece of rock and seeing how it responds to understanding how a mountain belt might be formed. So, last time we talked about stress, and I said again, it's the driver, it's what causes flow. And today we're going to talk about strain. It's the response that the material has. And you're going to see responses whether or not the material is a solid, like you might think this copper bar is a solid, or if the material is a fluid. And later on, down the road, we'll talk about strain rate, the rate of deformation. But for today, we're going to focus on strain. Again, it's a response that all materials have, and it's going to be, where you're familiar with it, is it's really what people would call elasticity. It's the elastic deformation. And we'll come back and reinforce that concept in a few minutes. So, we can talk about strain. We've already talked about normal stresses, and now we're going to talk about normal strains. If we apply a normal stress to a bar, it gets longer. If we deform it in tension, if we deform it in tension, we pull on it, the rod gets longer. If we push on it in compression, as here, the rod would get shorter. But it does two things. Really, this type of deformation goes on largely at constant volume. Not exactly constant volume for elastic deformation, but almost constant volume. And so if I pull on the rod to make it longer in tension, then the rod not only gets longer, but it gets skinnier. And we can see this in the second example where we do compression. If we compress the bar by pushing on it, it gets shorter, but it also gets fatter. Okay, so we have two strain elements that come into play in that kind of situation. We have the elongation, and if you go back and look at the coordinate system in the upper right-hand corner of the slide, we have an x1 going off horizontally, x2 going off vertically. So I'm going to call the strain in the vertical direction, I'm going to call it epsilon 2,2, and we'll talk about that notation for epsilon just like we did for stresses in just a moment. Okay, so the bar either gets longer, or not only gets longer or shorter, it also gets fatter or gets thinner. And so the strain in the vertical direction we're going to call epsilon 2,2. That's the elongation strain, corresponds to the 2-axis. And we're going to have a second strain, the epsilon 1,1 strain, which is the horizontal axis, and that's going to make the sample either get fatter or get thinner. All right, and there is a sign convention that's important in the earth sciences and in other fields, and that sign convention is that compressive stresses, such as shown on the right-hand side of this image, are called positive forces. And that's because we think about, as we go down in the earth, rocks are standing on top of us and we're being compressed. We like to think about that as being the normal thing that happens in the earth. In many other fields, in engineering fields, for example, tension is almost always considered to be positive. But in the earth sciences, compression is the positive direction. Okay, so why do we need to use strain rather than the length of the material? Okay, so there's a really simple demonstration. You can do this one at home. All you have to do is take apart your bike, take out the inner tube, cut it into small pieces, and you can do this demonstration at home. But I'll do it here. So here's a ruler. It's about 30 centimeters long, and there's a piece of my inner tube, one that had a hole in it, so I had to replace it. And if I pull on it, I can increase its length by about 50%. I can make it go from being about 15 centimeters long, and I pull as hard as I can make it up to about 23 centimeters. Now, it won't come to any surprise to you that if I take this piece of inner tube, which is twice as long, this is about almost 30 centimeters long, and I pull on it, I can make it about 45 centimeters long. So the amount of additional length I get is proportional to the starting length. And I have one more piece of inner tube, which is 3 times as long as the short one. If I pull on it, it increases also about 50%. So all of them increase about proportionally the same amount. And so the trick with strain is to normalize the amount of deformation, the length change, usually by the starting length. All right, and this is important because when we study, again, as with stress, when we study the flow of water or the deformation of a piece of granite or the deformation of dunites or peridotite in the mantle, we're going from studying small pieces of rock that we can hold in our hand to trying to apply that information to really large objects. And so we have to know, how do we scale properly? And the length scale is done by talking about strain. Okay, and there are several types of strain, and there's some terminology that we should get kind of on the same page about right out at the start. And one that I think many of you are familiar with is called simple shear, as illustrated in this diagram. If we take our square and we shear it in that direction, it will move and go from being a square to being a parallelogram as shown here. And we can calculate what's called the shear strain, which is just given by the change in x1, the amount that we've moved the sample, divided by this vertical distance x2, all right? And that change in strain is clearly just the tangent, or that strain ratio of those two numbers is clearly just the tangent of the angle psi. And if the strains are small, and most of the time we're going to be talking about small strains in this kind of discussion, and then we'll talk later about how to extend it to large strains, but for the moment we're talking about small strains. If the strain is small, you can approximate gamma, the shear strain, by the angle of rotation psi. Again, strictly it's the tangent of psi, but if you expand the tangent, the first order term is psi. It's interesting, and we'll come back and talk about this, but when you do this type of deformation, you not only get some deformation, some change of shape of the material, but you're also inducing a rigid body rotation. And when we talk about flow or about deformation, in general, we want to remove the rigid body part of the flow. And so if we express this deformation in terms of, as we will in a few minutes, in terms of the strain tensor, then the epsilon 1, 2 term, again referring back to our axes, the one axis being horizontal, the two axis being vertical, the strain part of it is just 1/2 times gamma, what one thinks of as the shear strain. In addition, there's a rotational component, omega, that's equal to 1/2 of psi. And so if you sum the true strain, epsilon 1, 2, with the rotational part, you get the full angular change. You get the full gamma. So you get 1/2 gamma here and 1/2 gamma with the epsilon part, and that gives you the full deformation. Okay, so again, what people refer to as simple shear in the geological literature really is composed of deformation plus rigid body rotation. We also talk about pure shear, and pure shear has kind of unfortunately two different definitions. One is in the mechanics literature, and the other resides in the geological literature. In the mechanics literature, one does a pure shear experiment, and you do that by sort of taking the tip of the square and pulling it out in this direction, or realistically the way you do it is you apply a shear stress here and a shear stress along that face, and you extend the sample as illustrated by the parallelogram. And now you've rotated about 2 angles. You have a psi up here, defined as we just defined before, and a second angle of rotation down here. And now the rotational part, the omega part, is just simply 1/2 times psi 2 minus psi 1. And if those 2 angles are equal, which is the definition of pure shear, is that those 2 angles have to be equal, then the rotational part is 0, and all the deformation is, or all the strain goes into doing deformation or goes into shape change. None of it goes into rigid body rotation. And so epsilon 1, 2 is equal to epsilon 2, 1, and we'll come back to the strain tensor in just a moment. It's just 1/2 times psi 1 plus psi 2. Okay, so that's kind of the way we think about this in mechanics. We have pure shear means that the 2 angles have to be the same. There's no rotational component, and the shear strain is given by the sum of the 2 rotational angles. Okay, but we'll come back and visit this again in a moment. In the geological literature, the system is quite different. When people talk about pure shear, they're talking about applying 2 compressive stresses, one larger than the other. And in the earth sciences, typically sigma 1,1 is taken to be the largest compressive stress. And since compressive stresses, again, are positive, we're going to mostly look at compressive stresses. And so sigma 1,1 is being applied here. Remember, here again is the x1 axis. Sigma 2,2 is being applied from the vertical direction, and 2,2 is smaller than sigma 1,1. And so if we press hard from the sides in the left-hand panel, then in the right-hand panel, we're going to see that the box gets skinnier, gets flattened, the width is smaller, and it's going to get lengthened. Okay, and we can talk both about the change in length and about the change in width, and we can calculate 2 strain components. The elongation in this case is epsilon 2,2. It's the change in length divided by the starting length. And the compressional, or the compressional component, epsilon 1,1, is going to be the change in width divided by the starting width. So once again, the way we get strains is we take the starting length and use that to normalize the change in length. So we always see something that looks like delta L over L, or if we were doing volumetric strains, it would be delta V over V. Okay, so we're going to use that approach now to examine the concept of strain. And again, it's to get rid of the idea that length is important and to really normalize things back to dimensions that don't care about whether I start it with a long piece of rubber or a short piece of rubber, that when I look at the strain, I get the same fundamental property out from the material. Okay, so one question is, what are the units of strain? Well, we said in the previous slide that strain is just the change in length divided by the length, right? And so this could be microns divided by microns or meters divided by meters. But whatever, the conclusion is that strain is a dimensionless quantity. So we don't have to worry about units. In the rest of the course, you're going to see Chris and I really talk to you a lot about being sure you keep track of units, know what units you're working in. But if you're working with strains, you're off the hook because it's a dimensionless quantity. All right, so strain tensor, just like the stress tensor, and the coordinates, just like we talked about. Coordinates, so we have a strain tensor. There are 9 elements in the strain tensor, just like there were 9 elements in the stress tensor. They represent strains along the principal axis and shear strains in the plane, exactly analogous to what we talked about for stresses. And again, as with stress, there's always a set of principal axes, shown over here, in which the strain tensor becomes diagonal, or only contains diagonal terms, and there are zeros in all the off-diagonal cases. So these are called the principal axes, and the resulting strains that go with them are called the principal strains. And much like with stresses, you can sum up the diagonal elements in either of these tensors. You take this set here or the set here, and you add them up, and they're equal to each other, first of all. And it turns out that they're also equal to the change in volume of the material divided by the volume. Okay, and this holds as long as the strain is small. And this is really an important point, that everything I've done up to now largely assumes that the strain is small, that this epsilon II term that you see in the center of your screen is a small quantity. And by small, we mean much, much less than 1. So remember again, the strain is change in length over length. And as long as I pull in this tube and I don't pull it very far, that the amount of lengthening divided by the initial length is small, I can get away with this approximation. But this statement holds only as long as the deformations are very, very small. Okay, and like the stress tensor, the strain tensor is symmetric, so there are a bunch of zeros off here when you have principal stresses down in the lower right-hand corner and the lower left-hand corner. For example, epsilon 2,1 and epsilon 1,2 are equal to each other, so that all the elements are symmetric, and rather than having 9 independent components, we only have to deal with 6. So we really only have to worry about the components that are in this upper sector of the strain tensor. Okay, well, I'm not going to spend a lot of time dragging you through this, but I did want to just sort of point out that it's very easy to calculate why the change in volume divided by the initial volume is equal to the sum of the diagonal elements, what are called the trace of the strain tensor, either in terms of non-principal or in terms of non-principal or in terms of principal elements of the strain tensor. And one can just look at this, the change in volume, along the equations along the left-hand side of the screen. The change in volume is just given by the initial, or the final volume minus the initial volume divided by the initial volume. We can set the initial volume equal to unity, and it could be meters squared, centimeters squared, centimeters cubed, microns cubed, meters cubed, whatever units you want to use, but we'll just make it 1 in whatever units we're using. And we can write out the change in volume over the initial volume. And since the initial volume is 1, it becomes a simple expression here. And we can write that out now. The final volume is just equal to, if we look at our red square over on the right, on the lower right-hand side of the screen, or a red cube, we can see that we extend each side of the cube. Each side of the cube was 1 initially, for example there. And we extend each side of the cube here in the 3 direction. We make an epsilon 3 extension. And so we can write the final volume as shown here in terms of taking 1 plus epsilon 1, this side, times 1 plus epsilon 2 times 1 plus epsilon 3. And if we do that, and then we multiply it out, and remembering epsilon is a really small quantity, it's much, much less than 1, we end up with that the final volume is equal to 1 plus epsilon 1 plus epsilon 1 plus epsilon 3. And then an expression that many of you probably are not familiar with, but there'll be other terms that are on the order of epsilon squared. But if epsilon is small, very much less than 1, then say it's 10 to the minus 3, then epsilon squared must be 10 to the minus 6. So if we want to worry about really small terms, we can simply throw away the terms that are in the order of epsilon squared, and we'll only keep this part of the expression. And terms that are in the order of epsilon squared are really, really tiny, we can ignore them. And so we end up with the change in volume over the initial volume is approximately equal to final volume, or is equal to the final volume minus 1, and that's equal to epsilon 1 plus epsilon 2 plus epsilon 3, as promised. Okay, so there's some caveats that I want to say out loud, and these will be reoccurring in the course as we talk through various parts of the class. And the first one is that isotropic materials, and we'll see this toward the end of the lecture today, that are I guess, the next lecture, that isotropic materials, that if you have a material that's isotropic, that is, if its properties are the same in any direction that you look at inside that material, then if you apply a normal stress, all you get is a normal strain. From the normal stress, you don't get shear strains. And likewise, if you apply a shear stress, you only get shear strains, you don't get any normal strains. So there's no coupling between what goes on in shear and what goes on from normal stresses. But in contrast, if you have an anisotropic material, things are quite different. If the material is anisotropic, and there's some really interesting problems in the earth sciences that rely on this, that if the material is anisotropic, then if you apply a normal stress, you can actually produce a shear strain. Or if you apply a shear stress, you can actually produce a normal strain, which means you can, in terms of fluids, if you think of fluid motion being driven by pressure gradients, like the water hose coming out the side of your house, the high pressure up by the house, low pressure out here by the garden, you apply high pressure and the water moves from high pressure to low pressure. Well, normally, if the material is isotropic, if you apply a shear stress, you won't cause any fluid to flow. But if the material is anisotropic, in fact, you do cause fluid to flow. And we'll return to this, particularly as applied to motion of magmas on the interior of the Earth. A couple of other caveats. If we have elastic deformation like we looked at in this piece of rubber, there is, in fact, a small change in volume that goes on. And it's not large and generally not important, but for many sort of large-scale applications. But there are places where that small change in volume is important. In plastic deformation or in flow, and quite in contrast, the assumption is, not the assumption, but the observation is that there is no change in volume. That flow, like if I took this rod and extended it from there to there, I might make it change its diameter, but I'd also change its length, and the volume of material wouldn't change. So plastic deformation or flow really takes place under constant volume conditions. And finally, many researchers talk about incompressible flow of fluids. In fact, that's really never quite exactly true. It's an approximation, because as soon as you touch a material, as soon as I touch this piece of rubber, as soon as I touch this piece of copper, I induce some deformation. It may be really small, and it's elastic, but anytime you touch any material, it will elastically deform. It may not flow, but it always deforms elastically. Okay, so we need to talk about one final issue while we're talking about strain, and that's the difference between finite strain and infinitesimal strain. Up to now, I've said we're making the approximation that epsilon, the strain, is really, really small. It's much, much less than 1. But in the Earth, we know that that's not always the case. I mean, if you build a mountain, rocks are going through strains of 2 or 3 or 5, 100%, 200%, 300% strain. And we have to know how to go from this infinitesimal strain and build it up to being a finite strain. And the way to think about this, I think, is to say, let's take a series of rods, like we have before, and we're going to pull on these. I'm going to fix them along the bottom, so the bottom is rigid and fixed. This part is fixed in each of the rods. And now I'm going to pull in the vertical direction. And the rod's going to get a little bit longer, and so if I go from the initial position 0 to position 1, I'm going to get a small change in length. And I could calculate the infinitesimal strain for that point. Then I can go to position 1 and think about it now as my starting condition. And I'm going to pull a little bit, and I'm going to go to condition 2. And the sample is going to get, again, a little bit longer. And so on. So I can go to 3, and I'll use 2 now as my starting position. And I'll go to 3, and I'll look at the change in length, and I'll divide it by the length that the bar was at when I was in stage 2. And so I can do this sort of mathematically by saying that the strain, what's called the true strain, or the finite strain, is just equal to the sum of all the little bits of strain that I build up as I pulled the rod and extended it just a little bit each time, and then I started over and extended it more, and started over and extended it more. I can build it up by summing up all the strain elements in these conditions going from I equals 0 to some value, how many times I want to pull it. And I'll sum them up as the change in length and saying going from step 2 to step 3 divided by the length that I had when I was in step 2. Okay, so that's just taking finite strain elements or infinitesimal strain elements and producing a finite strain. And of course, if you see this type of sum, your mind immediately pops to the idea that I could convert that to an integral. And so if the strain is large, okay, and large simply means it's not small, it means it's this less strain being much less than 1 no longer applies. I can then I can express this behavior in terms of an integral, as I have here. And if we take this expression from the summation, I end up with the integral from the starting length to the final length of the bar. So I start here, and I start there, there's L0, and now I'm on L final. And I get there by summing up a bunch of small steps along the way. Then I end up that the true strain is the natural log of the final length divided by the initial length. Okay, so we have two terms. We have finite strain, infinitesimal strain. So we go from infinitesimal strains, we add those up to get the finite strain. And these have other terms that are often used in the literature or in daily language. The infinitesimal strain is often called the engineering strain. And the large strain, the finite strain, is often called the true strain. Okay, so a quick question. Which of the two strains gives you the larger value? Suppose I take this piece of rubber and I pull on it and I say I could double its length. And now I'm going to calculate the true strain for that expression from this log term that's down in the lower right-hand part of the slide. And I want to compare that to the engineering strain, calculated by just looking at the change in length divided by the length. Okay, so if I double the length of the rod, or double the length of this piece of inner tube, and I want to ask which gives me the greater strain, engineering strain or finite strain. We can do the calculations easily. The engineering strain is in the first line here. And if I change the length from 1 and make it 2 in length, and divide that by the initial length, I get a strain of 1, which is a strain of 100%, same terminology. If I calculate the true strain in the second line, and I do the integration, get the log of 2L over L, so that's a log of 2, which is 0.7. That corresponds to 70% strain. So the answer is that engineering strain will kind of over-express the amount of strain that took place. True strains are always smaller than engineering strain. And I thought we could ask this question in one other way. And we can do that by saying, at what point, if I'm doing experiments in the lab and I want to be able to take these from the lab to the field, I want to know, yeah, maybe I can get away using engineering strain, but how long can I do that? And so we can ask the question, at what point do engineering strain and true strain deviate by 10%? Okay, and maybe I can live with a 10% error, but I certainly don't want a 50% error in my calculation. Or you could say maybe I want a 1% error, and we could see how much strain I can acquire before I reach a 1% difference between the engineering strain and the true strain. But I'm going to ask the question for 10% strain. And to do that, I made a plot that shows the true strain versus engineering strain. And the dotted line running up the center here, along here, is a line where one would fall if the engineering strain and the true strain gave you exactly the same result. But what we see is that the true strain, plotted here, look at the dark line, the dark solid line here, the true strain always is smaller than the engineering strain. And if we take the true strain out to 20%, and we look at what the engineering strain is, it turns out to be 22%. And that's a 10% difference. So if I can live with 10% uncertainty in my calculations, I can go out to strains of about 20% before I have that type of error introduced into my calculation. So that's kind of the story about strain and stress, and we'll see the coupling between the two in the next slide, or the next video. We're going to talk about how do we now link what we know about stresses to what we know about strains. How do we couple these two tensors, these two 9-element arrays that we have to deal with?